Thank you very much, Alexei, for you are helping to show the way to get us there one molecule at a time, and that's the way to do it. So thank you so much. Our final speaker before our lunch break is Dr. Dennis Smith, who's going to be speaking to us on the topic of nanomedical, polymer, and composite science and technology. Professor Smith holds a bachelor's degree in chemistry from Missouri State University, as well as a PhD in polymer chemistry from the University of Florida. Dennis was a Rhone Poulain Research Fellow in Lyon, France, and recipient of the 1997 Dow Chemical Company Central Research Inventor of the Year Award back in 1998. Dr. Smith holds 13 U.S. patents with an additional 9 disclosed or pending, and has published or been referenced in more than 90 papers and over 200 conference papers. And I have a feeling that we're going to add to that number after this conference. Welcome to the conference, Dr. Smith.
Well, thank you very much. I'm glad to be here. I've never been in this part of Canada before, so it's quite beautiful. And I didn't pay attention to the instructions, so let me see. All right. Well, I'm the last thing before lunch, so I've heard several complaints already that you're hungry, so I'm going to try to make up some of the time. I've got a lot of slides here. I didn't know exactly what to put in this. I'm a little bit of a fish out of the water. I think I'm the token synthetic organic polymer chemist, which is a great thing for me because when I look at this crowd, I see collaborators and people that need new materials and advances in nanomaterials. So nanomedical, polymer, and composite and science and technology. I really am not going to talk much about nanomedical at all, but I'm going to show you some examples primarily from our Center for Optical Materials Science and Engineering Technologies at Clemson, where we focus on a lot of nanotechnologies, primarily nanoparticles and polymers, which self-assemble and give you interesting optical responses. So also collaborating with a company, my little disclosure here, as we've seen before, Tetramer Technologies was founded in 2001 by myself and 2 other faculty at Clemson, and it's quite a nice little venture. So nanomedical, what does that mean? What does that conjure up in your mind? For me, it goes to my favorite Dilbert cartoon, absolutely. So it's about capital. I mean, this is a tremendous opportunity. So Dilbert here, take my money from the venture capitalists. Don't you want to hear the rest? No, I don't need to. I have a product. Well, I need the forklifts and massage oil then. So this is Dilbert's little nanoparticle, nano product. So regardless if it's capital from venture capitalists or capital from the NIH, it's a great opportunity, and the market drivers are very important that we should recognize. So where's Clemson? Clemson is just on this same mountain range, I think, but just down here. Our state motto is Smiling Faces, Beautiful Places, which is much better than the old state motto, which was the secession state. So we have a brand new building. It's the Advanced Materials Research Laboratory, where we do a whole host of things that concerns nanomaterial science as well. We have an expertise in fluoropolymers, which I'll show you a little bit. Photonics materials, of course, fiber optics. There's a fiber optic draw tower there. And we do fuel cell materials, of course, related back to fluoropolymers as our photonic materials, and this growing area in renewable materials, and I'll show examples from some of that. I do a lot of work with the ACS and the polymer division. If you go to polyacs.org, you can find out a lot of nice nano-focus type conferences and workshops. These are some of the ones that I'm involved in at the moment. So this is kind of a little quad chart for our laboratory. We have 3 distinct platforms, I like to call them. Perfluorocyclobutylpolymers, which I'll touch on just a little bit. I'll try to lay off the heavy chemistry as much as possible. We heard a lot about carbon and carbon allotropes already, so I'm going to show you a little bit from this work on making carbon and micro and nanostructures from carbon. And then renewable resource polymers is a growing area, and for this crowd, we do some tissue engineering. We make materials with specific cell affinities, and I'll show a little bit of that as well. Green materials, and basically, for the most part, focused on lactide. I'd like to back up a little bit and look at my favorite quote. This is one of, everybody in my community knows this quote. It's a very famous quote, and it's good for this crowd because I think we are in nanoscience where polymer chemistry was in the 20s, not too long ago. This was a we think we know who said this, but it's a famous quote. "Dear colleague, leave the concept of large molecules well alone. There can be no such thing as a macromolecule." This was advice given to our pioneer of our area, Hermann Staudinger, in 1920. So the concept that a macromolecule could even exist was debated. And we knew a lot about organic chemistry in 1920. There was a thriving industry in organic chemistry. So here's another one that some of you might know. So contrast from 1920 up to the 1960s, and we see this revolution in synthetic organic materials, polymer-based materials. So so he was vindicated finally, Nobel Prize, after being ran out of Germany and ended up at the ETH in Zurich. They won the Nobel Prize in 1953 for actually proving the existence. And actually it was Mark, I digress a little bit, Mark that was attributed to that quote, who actually proved the existence of macromolecules through X-ray diffraction. So with that, macromolecular architecture was born, and we were very rapidly able to make simple compounds like this, where we have a mixture of different types of molecules. This is a tri-block copolymer, an ABA tri-block copolymer. It's a commercial material, Kraton rubber by Shell. And so you have a polybutadiene phase, which doesn't like the polystyrene phase, so these things self-assemble on the nanoscale. They give you very rigid spheres dispersed in this rubbery group, and so we didn't call that self-assembly when this first was done. We called it micro and nanophase separation. But it is self-assembly, and so you can make a rubber. You can have a synthetic rubber. Or if you want to think about using this directed assembly, which is done today, IBM just made a nice announcement, it was late last year, on building lithographic chips, or building chips through lithography based not on photolithography definability, but on self-assembly of block copolymers. So where you actually have nanophase separation, nanophase lamellae, or spheres or columns, depending on where you want to hit this phase diagram. And then you can do specific reaction chemistry at some of those different phases and then get lithography. So you can start directing assembly to form structures using block copolymers. And we had some good talks about mention of peptides, polypeptides. Got to mention Bruce Merrifield, who won the Nobel Prize in 1994. And this is a little nano machine. These are microparticles, spheres with clearly defined reactivity on the surfaces, which do lots of little oligomerization and polymerization reactions on the surface. And so this is the basis of PCR. And then another Nobel that I'd like to point out in polymers is de Gennes, who actually we lost last year. And he laid out all the fundamentals of really self-assembly for liquid crystals, which are, again, a nano phenomenon. And then most recently, to do with nanoscience, of course, is the Nobel Prize in 2000 for conductive polymers. And really, we know now that the conductive polymers used in photovoltaic cells and in light-emitting diodes for display applications all depend on the nanomorphology and the mixing of the different phases. Hole transport and electron transport layers. I'm going to skip some of these. Now, we got into this area working at, this is actually some skunk work that we did. It wasn't funded by anybody, but we had a nice expertise in carbon nanotubes at Clemson, and so somebody had the nice idea of, hey, and we had a nice expertise in polyaniline, which is a commercial conductive polymer. And we decided to, hey, let's put them together. Polyaniline is a really interesting material. And it turns out that this is the actual title of this paper, and it remains like my most cited reference. It never was funded. We never did anything more. But it shows you the reactivity of these particles. So this is carbon nanotube doped polyaniline. You can get conductivities of polyaniline with very, very little doping of carbon nanotubes, 100-fold increases in conductivity. And this is clearly doped reactions by the defect areas or whatever. But that's something I want you to keep in mind, is these nanoparticles, nanomaterials that we're using are actually reactive, and we can do a lot of chemistry with them. We've also found, this is a patented technology, dispersing nanomaterials in fluoropolymers or halogenated polymers in general. That's a very, very efficient way to disperse nanoparticles. This just shows an example of excellent dispersion and even single-wall carbon nanotubes found in this fluoropolymer. And with that, some very nice technology is coming out of Tetramer Technologies and Clemson on using carbon nanotubes, very, very low levels, 0.05% in some cases, 0.05 weight percent, 0.005 weight percent of carbon nanotubes in semicrystalline piezoelectric polymers such as polyvinylidene difluoride, which is a PVDF copolymers, which are commercial. They have a piezoelectric response. You put a little bit of carbon nanotubes in this, and they increase 7-fold. And this is very interesting for energy harvesting applications. So we don't understand this at all. We don't understand how this is happening, how it's affecting the piezoelectric crystalline phase. But very interesting. Again, proactive effects of these nanoparticles. So here's an application of that. We were working with Nader Jalili at Clemson. He's in the mechanical engineering department. And so he can electrospin fabrics of VDF with these carbon nanotubes in them. And we can address things. We can start looking at things like wound healing, bandages, or just fabrics which harvest electricity and power batteries. I'll skip this. There's a lot of nice nano sensing work going on by Tony Giuseppe at Clemson University. He actually has an implantable device which senses oxygen and glucose for the warfighter. It's a DOD, and it relates back the trauma condition of people in the battlefield. And it's a nice technology. So our renewable resource platform focuses on lactide primarily, and I'll point out some of that. We like cotton, the USDA cotton quality laboratories at Clemson, so we like to do cotton. And this is, of course, lactide monomer is a commercial monomer made from lactic acid, which is made by the fermentation of corn sugar. So there's a lot of promise in lactide, and it's bioabsorbable. So we can make electrospun fibers of this, we can make nonwoven mats, and all types of things. Some lactide ventures, just to show, I work with bioengineers and other people to try to tune the affinity of these bioabsorbable materials and to cells, to different cells. So we look at lots of different types of copolymers. We try to use commercial materials. These are commercial oligoethylene alcohols. And we also look at these bacteria-produced polyhydroxyalkanoates, which are also commercial biometabolics. So this just shows a little bit of the cell studies. We can by comonomer incorporation, we can do electrospinning to get much more surface area, and then we can tune cell affinities by changing just the comonomer relationship just a little bit. This is my favorite one, though. This is something very recently we've done. People look at this and say, "What are you doing? You're putting a fluorocarbon into a green material, lactide." Well, we call this where green meets mean. So we have a lactide. This is our nice, happy green material from lactic acid. And then we have these, which are commercial from Solvay, Solexus, or DuPont. They're perfluoropolyethers, and they're primary alcohols. Well, that's what you need to ring open polymerized lactide. So you can make, again, a tri-block copolymer. And these will self-assemble at the nanophase and then give you very, very interesting properties. And so extremely low contents of this perfluoropolyether changes the properties of this PLA tremendously. Just for an example, this is PLA quenched. It's a semicrystalline polymer, but you can quench it so that it's clear. And then here are the copolymers, optically clear, very good miscibility, and these are the corresponding blends, which of course phase separate. And the fluorocarbon goes to the surface. This is what's interesting. So after about 1 weight percent of this perfluoropolyether blooms to the surface, forms a nano-structured, nano-roughening on the surface, and gives you tremendous drops in water contact angle and increases in surface energy right away with just a little bit. So what's the impact on this in a tissue engineering material? Well, now you've got something that you can really, really tune the bioabsorbability of. So the hydrolytic stability or the enzymatic stability by tuning this, putting a little bit of this fluorocarbon in there changes the degradation rates tremendously. Now I'm going to talk a little bit about this technology. You don't have to worry about the chemistry, but we have a processable. This means micromolding, or we can do nanomolding as well. So you can make these resins, which you just heat them up, and they form glassy carbon or this polynaphthalene network. So this is an allotrope of carbon, like we've heard before, not diamond. It would be great if we could do a polymer precursor to diamond. But this is extremely efficient. So if you need a glassy carbon microstructure or nanostructure, this is one of the best efficient-wise, yield-wise, from a polymer precursor, then it's processable. So it's not like polyacrylonitrile, which we make commercial carbon fiber from. That's hardly processable at all. And it's about 50% yield, carbon yield, after you pyrolyze it. This can be up to 80+% yield. So what we do is we've made lots of nice microstructures, and this is actually our first look at soft lithography. We did this with George Whitesides with stamping approach. He taught us all about that. And then I'll focus, we can do submicron gratings. That's easy. We did some rods with the Air Force. But this is a good, simple resin material if you need a carbon structure. The other thing is it's a very reactive group. You can polymerize these things, and it's all radical chemistry, but they're very reactive radicals. And of course, they react with C60. What radical doesn't? But carbon nano onions, which we have an expertise in at Clemson, which are normally not very reactive because these are about 20 layers of concentric buckyballs, and these outer ones are not very reactive because they look like graphite to the radical, which isn't very reactive. You have to have some of that ring strain in order to get that radical to attack. But we found that you can actually react these carbon nano onions and get them solubilized. So we can solubilize them, we can process them, we can move them around. This shows a TEM image of a carbon nano onion that has been through a filter, and we can now burn off the polymer through some clever oxidative conditions and leave these carbon nano onions. So now we've got a way to actually manipulate these nanoparticles, which are reactive. And in addition, the BODM, or the monomers that we have, are selective for certain sizes. So it's a way to resolve these too. So I think this is actually going in a direction, and we have some people that are very interested in this. This is going in a direction to actually, as a delivery mechanism for putting these carbon nano onions in the right spot. So again, nano manufacturing approach. And we're using these in photovoltaics as well. But as far as nano molding goes, we can take these very, very processable resins and take something like a silica opal, which you can make. You can buy the silica spheres and close pack them and let them arrange in a hexagonal array, or you can make them. And so we've done that. Here you got an opalescence from this little close packed silica spheres, or monodisperse. And then you could take your monomer and you can impregnate all these void volume. Of course, the color changes because you've changed the dielectric contrast, and it's a photonic crystal. And so the color changes, and this has been pyrolyzed, and then you can simply etch out the silica and leave the periodicity. So now you've got a very active carbon surface that has nano periodicity, and it could be used as a sensor or some other device. We've actually done some things with hemoglobin. You can use it as an oxygen sensor, but basically the optical analogy to Bragg's law, of course, is the photonic band gap, and that any refractive index change on this surface gives you a corresponding reflection or diffraction wavelength. So you can just change very simple water to acetonitrile. So very, very modest changes in refractive index can give you very reproducible changes in the rejection wavelength. And this is not new. Of course, photonic crystals are all through nature. The brightest colors that we see are nanostructures and optical diffraction on those. This is just a feather from my yard. I picked it up. Of course, in transmission, you don't see anything. But in reflection, you see these beautiful, nice blue colors here, which are, of course, nanostructures in the feather, a periodicity, a nanoperiodicity, just below the wavelength of visible light. Of course, opals, peacocks, and then, of course, lots of people are using this to build waveguides, because a certain wavelength designed for this trench cannot exist in this photonic bandgap material. So very, 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 very good, efficient optical communication devices could be used. So this can be done very simply with polystyrene spheres. So you can make monodispersed polystyrene spheres. This is simple. It's latex chemistry. It's been known since the 50s. And you can get these things to order. Now, this is not a closed Pax array. This has got electrostatic repulsion because there's a little negative charge on these particles. And so they will have different colors depending on the concentration. And this is just a simple diffraction of light. So we've been able to do this and actually encapsulate this crystalline colloidal array, as they're called, with a thermoplastic matrix or a thermosetting matrix, a hydrogel, and then back out, dehydrate that, and then fill it back with a rubber material, like a polymethyl methacrylate material, and then get clearly different responses based on load. And then what you're doing, of course, is just changing the d-spacing between these particles, and you get clear color changes, and it's mechanochromic. This just shows no load. You get one wavelength rejected, and then compression, you switch that, and then, of course, goes back. And this is actually the TEM images of some of these composites, and you can see unbelievable order. This is just electrostatic ordering, and then dehydration, backfilling with another material, and cross-linking it. As you can see, there's defect areas here, but fascinating. It's just polystyrene, and these you can get dramatic color changes in just 4% loading of polystyrene spheres in these cheap thermoset plastics. Of course, mechanochromism is just changing the despacing. Well, you can do the same thing with solvodochromism and make a chemical sensor. So this is the optical nose, like the electronic nose, where you change the solvent has a certain affinity for a polymer, changes the conductivity of a carbon black filled polymer. This is changing the optical response of a polystyrene ordered material in a polymer matrix. And so we were able to actually do different types of templating and actually photopolymerize different designs inside of this material as well, and make it solvodochromic. And pick, depending on the despacing and the swelling, we can pick the color. So I'd just like to preview just quickly some of this work that actually was commercialized by Dow at one point, and then they got out of that, and I took it to Clemson and actually used it for optical materials. This is a very unique type of fluoropolymer. So it's a semi-fluorinated polymer. It's very functional, very processable, and we can put lots of different things on this to make it a good host for nanomaterials. Very optically clear. So optical materials is really where we went from this. And so what we do is we build monomers with different functional spacers, and we use some of these. This POS, which I'll mention later, is an actual nanoparticle. I call it a molecule. It's a big molecule. It's well-defined, but it's a nano-size thing. And we can put those in here in good design. This is a review paper that we just came out late last year, if you want to look at this in any detail. But very easy processability for a fluoropolymer. So you get fluoropolymer, fluorinated material type optical properties and thermal and oxidative resistance, chemical, and so on. But it's extremely processable due to the flexible nature of that backbone and that perfluorocyclobutane ring. So lots of collaborators actually here in Canada, the research center, and the Canadian Research Center, they've actually did this. This was their arrayed waveguide that they did by reactive ion etching. All right, I'll skip that. So direct embossing is what we're doing now, and we think there's some good applications for actually particle manufacturing using this technology, because nothing sticks to a fluoropolymer, so you can actually put in some type of nano structure. Of course, these are just microstructures, but you can put in a nanostructure and then make nanoparticles, which I'll show at the end of the talk. I'm going to show some results from my good friend Professor DeSimone at UNC Chapel Hill on some of his technology. So dispersing different types of chromophores in these polymers is very easy to do. Like I said, there's a patent on nanomaterials and halogenated polymers. And I think there's a lot to this. Halogenated polymers, semi-halogenated polymers. And one other thing we can do is we can build a type of chromophores which have specific binding affinities for particular anions. And this just shows, this is a nice optical sensor that Scott Icono in my lab recently developed. So it's got this nice little bithiophene. It's a semi-fluorinated polymer, and it's very photoluminescent anyway. But what happens is when it comes in contact with fluoride and cyanide, and you can see iodide to some extent, you get a turn-on fluorescence, which is nice. Most optical sensors, chem biosensors, are turn-off fluorescence, quenching fluorescence. But this is a turn-on, brilliantly turning on fluorescence, optical fluorescence. For fluoride, which is important for a lot of safe water, and it's also a hydrolysis byproduct of sarin and some other bad actors. Of course, cyanide as well. So we do lots of different incorporation. You can see rare earths, erbium, because it gives a fluorescence in the near IR, and it's what's used in optical amplification commercially today. So we like to do rare earths, and we also like to use this guy. I don't know if people are familiar with this, but this is a really nice additive nanomaterial in my field. It's called polyoctahedral silsesquioxanes, or POS, P-O-S-S. And I'd like to give you a little bit of background on that. This all comes from bioinspired or biomimetic type of materials design, because lots of people are trying to do that. These are all CVD type fabrications or E-beam lithography to try to mimic what the lotus leaf has, the fly, of course the spiders or the gecko feet. Okay, you can try to build these nano microstructures and try to get bio-inspired properties, and that's what we try to do with these POS materials. They bloom to the surface and they give you nano roughening, and we know enough about the lotus leaf and self-cleaning and ultra hydrophobicity, ultra oleophobicity, to know that it's not about micro roughening, it's about nano roughening. You got to have the right type of surface roughening, and you throw in a little inherently low surface energy bonds like fluorocarbons, so you get a synergistic effect. And we've been working with this. This is funded by the Air Force. The U.S. Air Force actually commercialized this material. It came out of AFRL at Wright-Patterson Air Force Base. And mostly my student, who's a captain in the U.S. Air Force, is graduating next month, sadly. He's done all this work. But they've been commercialized by this hybrid plastics company. They're actually in F-22 fighter canopies, very atomic oxygen resistant. They are extremely abrasive resistant, but we want to use them in a much more subtle way. Our first entry into this was to use this octa-anilino, and you can make these. These are not very difficult to make, and actually they're natural as well. They're found. You can find these POS cages in different sizes in rice husks, so they're renewable. It's a renewable resource as well. But you can make these. This octa-anilino was provided by Rick Lane, University of Michigan, and then we could put on a nice polymerizable group and make different types of composites. So most recently, through our Air Force collaboration, we were able to make these Scott and Joe Mabry at Edwards Air Force made it, these alkyl fluoroalkyl derivatives. Now, that's the nice thing about POS is that here's the POS cage, and you can really change the functionality here. So I think for the nanomedical people, this basic building nanostructure is something that you want to consider. But you can change it. You can change that functionality. So this is actually an X-ray crystal structure of this fluoroalkyl group. So we've been putting that into our polymers, and we get a dramatic, this doesn't look like a dramatic number if you think about hydrophobicity numbers, but 160% increase in oleophobicity, this is hexadecane, is really, really good, and that's what the Air Force wants. They want something that's really going to be resistant to the jet fuel. So, and you can see, why is it? Well, here's the AFM image. You get this nice nano roughening. So you get the synergistic effect of the fluorocarbons sticking up at the surface, blooming to the surface, and then this POS material, whether the POS is actually on the surface or is it just bulging the polymer up a little bit, you get this effect. You also get a nice modest increase in oleophobicity or hydrophobicity. So we've done, we try to take this approach and we hook on POS covalently, not just blend it in. And we've done that, and there's a couple of papers last year on that. And we can see this nano roughening. Okay, just a little bit about optical properties in our Composite group. We make a lot of these core shell particles. These are lanthanum fluorides or erbium or europium, and we tune these particles for specific functions to give us fluorescence in the areas that we want. And here's just an example. This is in our one of our fluoropolymers. This is loaded up with these lanthanum fluorides, and they're still completely optically clear. So these little cluster compounds, they're nanoparticles if you want to call them. Inorganic chemists call them clusters. But they're small little clusters of a few dozen complexes, molecular complex, so a few dozen nuclei, metal nuclei. And they're dispersing so well, there's no aggregation, so that you get this optical clarity in the polymer as well. So then you still get this nice 1550 emission that you want to see from erbium. And I'll skip that. Now, quantum dots. I'll just end up on a little bit about quantum dots. So nanoparticles disperse into these fluoropolymers. So we got to try quantum dots. This is actually something that Lucent led, and they have their first patent on it. And then we started working with Lucent. But this just is an example. You never want to load up 20% weight percent of lead sulfide nanoparticles in a polymer, but this just shows the TM image of some really, really nice dispersion. These are just dumped in there. There's no actual special capping chemistry on the surface. So you might know about quantum dots. There's a lot of biomedical applications of quantum dots. That's really the biggest area for quantum dots. And they're just semiconductor particles that change their fluorescence based on size. This is quantum confinement, particle in a box. So it's not fluorescence as we like to think about promoting electrons to another state, and then a photon comes out when they come down. But they get sucked up by cells, and you can do lots of bioimaging that way too. And then you can see different colors, different types of, this is only 0.9 weight percent ocean nanotech quantum dots. These are commercially available in one of Tetramer Technologies plastics. And you get very bright colors, very, very, very low percent incorporation. We're also using these for white light emission. Okay, I'm going to skip, I think I'm done, pretty much done. I'm going to show you just one part of Joe DeSimone's work. This is print. This is a company that Joe DeSimone founded a while back. It's called Liquidia. And it's really about using fluoropolymers. He's one of my fluoropolymer colleagues. Using fluoropolymers to actually fabricate nanoparticles. And this is a thermosetting fluoropolymer technology, and you can get unbelievable fidelity to a photolithographically defined mask of some sort, or photolithographically defined structure, and then you get to an unbelievable fidelity, and then you can actually manufacture some of these particles. You can measure, and then he harvests these particles, and then what they're doing is what's really interesting is putting these in the presence of cells, and the cells gobble them up. They eat these nanoparticles like crazy. So different sizes, different shapes you can do. There's different materials, and then let me see. This is just one example of a cell just eating up these fluorescent. These are fluorescent tagged particles. But he has a video of, I think it's on the website of Liquidia, and you can see these cells just gobbling these nanoparticles up. So with that, I will thank my collaborators, and I'll thank my group, and I'll thank you for your attention.